It's a historic moment. We're going to discuss exclusively Ampere's law as it was amended by Maxwell. This genius who recognized that a changing electric field can cause a magnetic field. We will see some remarkable examples why that was necessary. And out of that, of course, came this fabulous victory of the theory. You will see that later in the course, that it not only predicts the existence of electromagnetic radiation, but it even predicts that the speed of light of all electromagnetic radiation is 1 over the square root of mu 0 times epsilon 0. A remarkable victory. And it turned out that that's what it was. Before I go into the specific problems, I want to do with you a classic which covers effectively all conceivable problems. All conceivable problems with this new concept of displacement current. And then we'll do the problems. Let's first write down the new equation. Closed loop integral of B dot dl equals mu 0 times I through plus mu 0 times epsilon 0 times d dt times the integral of E dot dA. What does this mean? It means that you must choose a closed loop. Any closed loop is fine. Of course, if you don't choose a clever loop, the equation still holds, but it doesn't do you any good because you've got to introduce symmetry. Otherwise you can't solve a problem. But any loop in principle will do. Then you attach to that closed loop an open surface. It's open. Does it have to be flat? No. It can be a bag, like a shopping bag. So this could be the closed loop, and you could have a surface like a hat you can put over your head. And we will do that today. I through is the current that poked through that surface. The whole concept of a current going through a loop is nonsense. This is an electric flux, and this is the time derivative of that electric flux. And this is the time derivative of electric flux going through that open surface. So now I come with my classic problem. Here is my classic problem. Let's keep this equation a little bit at hand. I have a capacitor. This is not a problem on your assignment, although you have similar ones. Let's assume that the plates are circular. That makes it a little easy to calculate things. And let's assume that the radius of the plates is r. So the area of each plate is pi r squared. We are charging this capacitor with a constant current. IC. So the inside here becomes positively charged and is growing the charge. And so you get an electric field which is pointing in this direction. And this electric field E is growing in time because more and more charge accumulates. We will make a simplified assumption that the electric field is constant between the capacitor plates. It's not true, but it will be our assumption, and that E outside the capacitor equals 0. We'll make that assumption. Now I'm asking you 3 questions. What is the magnetic field at a point P1 at a distance r from the wire, whereby for P1 r equals larger than r? And I want to know the same for a point P2, which is inside the capacitors, at least if I have a plane perpendicular to the wire, that plane would completely go through the capacitor, between the capacitor plates. So also for P2, R is larger than R. And then I'm going to ask you, what is the magnetic field at point 3, which is at a distance R from the center line, whereby R is smaller or equal than R. You can also put equal signs here. That is our goal. Let's first take P1. It's completely classic. You don't even need Maxwell's new equation. You simply take Ampere's law. If this is your point P1, you choose as your closed loop a circle which is completely symmetric relative to the wire. You choose a flat surface. There's no reason why you would not do that here. There is a conduction current IC coming in here, and there is a conduction current IC coming out there. This is a surface, and a current is penetrating that surface. If we look from the left, we know that the magnetic field will be going around clockwise. So if I look at the current going away from me, by convention, the magnetic field will be going around in circles, symmetric about the central line. And of course, if I choose a circle, concentric circle, the B field will be the same everywhere because it has the same distance to the wire. Clockwise, when the current goes away from me, counterclockwise, when the current comes to me, it's a convention. So I don't worry even about the direction anymore. I know the direction already. So I don't even worry about signs too much. I'm only interested now in the magnitude. So I apply Ampere's law. There is no changing magnetic flux, electric flux going through this surface which I have here. So I'm only dealing with this term. This term is 0. This is the only term I have. So I get B times 2 pi R equals mu0 times the conduction current, and we get a result that we have seen before, mu0 IC divided by 2 pi R. Magnetic field falls off as 1 over R, and seen from the left side, it goes around clockwise. Now let's go to point P2. With point P2, I'm going to make exactly the same. I will have here the capacitor plates. Here are the current wires. Here is point P2. Again, I'm going to make a circle, concentric circle, and the radius here is R. This is point P2. I now have a choice. Well, I have lots of choices, but I have now two obvious choices for the surface. The open surface attached to the loop. One would be this, and another one would be this. It's like a shopping bag. It's open here, I can stick my hand in here, and here is the surface. This is that surface. In the first case, I have no contribution due to the conduction current, because there is no current going through this, no conduction current. In the second case, here, this term is 0. By the way, this term has a name. We call this term the displacement current. It's a misnomer, but that's what it's called. It has the same dimension as I through, amperes. There is no displacement current going through this surface, but there is only going a conduction current going through that surface. Whether I apply a flat surface or this bag surface, I should get the same answer. Well, be my guest. I don't care which one we do first. let's first do the bagged surface. If we do the bagged surface, then we get B times 2 pi r, closed loop integral along this line, equals mu 0 times the conduction current poking through the surface, which is IC. And there is no changing electric field anywhere going through the surface, because remember, E was 0 here. And we have assumed that E was 0 here, outside the capacitor. And this is open here. There is no surface here. So what do you find? B equals mu 0 times IC divided by 2 pi r. You find exactly the same result that you found for point P1. So this is R larger than R, or equal to R, and you are in the plane between the capacitors. You are at point P2. Exactly the same result. And that shouldn't surprise you. Now we're going to use this surface as our surface, open surface attached to this wire. And we better get the same result. But now the calculation is a little bit more complicated. I have an electric field, and the electric field is running from left to right, and it is growing. And the reason why it's growing is that the charge that piles up here is of course increasing. If the current were constant, then it is increasing linearly in time. What is that electric field? Well, that electric field is sigma, which is the surface charge density, divided by epsilon 0. And it is increasing in time, so surely the EDT is not going to be 0. In fact, the EDT is going to be a constant. Well, how do I calculate now the changing electric flux through this surface? I'm going to make a slightly different drawing. This is a circle with radius capital R. So that's the capacitor plates. And this is the circle through which point P2 goes. And outside the capacitor plates, E equals 0. And inside the capacitor plates, if I look from right to left, I see a constant but growing E field. And this now is my flat surface. And there is no conduction current going through here. Now I have to do the closed loop integral of B dot dl. B times 2 pi r equals mu 0 epsilon 0 ddt integral E dot dA. And this is the surface, and E and dA are in the same direction, so I can immediately drop the dot product. What is E as a function of t between the capacitor plates? That is sigma, which is changing with t, divided by epsilon 0, which is the charge divided by epsilon 0 times the area between the plates, which is pi r squared. Q of t is growing linearly in time. At time t equals 0, it is Q0 plus the conduction current times t. And therefore, dE dt equals dQ dt divided by epsilon 0 pi r squared. But the dQ dt itself is the conduction current. So this is the conduction current divided by epsilon 0 times pi r squared. And it is constant here because I of C, the conduction current, is not changing. Later today we'll see a problem whereby the conduction current is changing. Here it's not, it's constant. All right, so we're well on our way now. We now have to integrate, we have to calculate this term. If we take mu 0, epsilon 0, this term now simply becomes dE dt times the area, because the dot disappears, they are the same direction, times pi r squared. But we know this. We just calculated that. And notice you have downstairs here epsilon 0 pi r squared, and you have upstairs here epsilon 0 pi r squared. So what do you get? This term becomes simply mu 0 times I of C. And therefore, your magnetic field B at that location P2, where R is larger than R, between the capacitor plates, equals mu 0 IC divided by 2 pi R. And that is exactly what we found before, and that should not come as a surprise. In other words, the induction current, I of D, is exactly the same as the conduction current, the displacement current. This is the displacement current. It is the total displacement current. Total because I have chosen the displacement current to go through this entire surface. If later we're going to calculate the displacement current through a smaller flat surface, then it will of course be smaller. But in this case, the total displacement current going through this surface, which covers the entire surface of the capacitor plates, that displacement current is the same as the conduction current, and that of course is a requirement, because if not, you would never see the same answer for the magnetic field at point P2, whether you take the bag surface or whether you take the flat surface. So you had a choice, the bag surface or the flat surface. It's clear that the bag surface goes a little faster, but in any case, you see you get the same answer. So now what we have left the magnetic field between the capacitor plates for a radius which is smaller than the radius of the plates. So here we have the plates, now we have a radius little r. Of course our closed loop integral is again going to be a concentric circle. We have a conduction current going in here, and we have a conduction going in here, and we have here in between a growing electric field. And now you may think that you have options about the choice of the surface that you attach to this closed loop. It's true, you have an option. If you think you're going to be very clever, you may choose a surface which runs parallel here to E, then curves like a shopping bag, and here runs parallel to E. So it's open. It's an open surface here. You can stick your hand in. And you may say that the electric flux going through this portion is 0 because E is parallel to dA. Excuse me, it's perpendicular to dA, because the dA would be in this direction, E is in this direction, so the dot product would disappear. So you will say, aha, all I deal with is the current coming out here. But that's not true. Because as the current charges up this plate, there is also current going up in this direction, and there is current going onto the plate like this. Therefore there is current going down here, and there is current coming down from the plates here. And that current is penetrating this surface, and you would have to take that into account. Now, if you find an easy way to calculate that current, be my guest, and I'm sure you will get the right answer. I prefer not to do it this way. Now you may be clever and say, aha, now I'm going to choose a surface which is completely bypassing the plates, and which goes like this. Wonderful. I have here now conduction current penetrating through the surface here. But what do I have here? Through this part of the surface and through this part of the surface, as long as I'm inside the capacitor, there is a changing electric flux, which now I have to take into account. So not only is the second term of Maxwell's equation not 0 due to this conduction current, but not only is the first term not 0, but the second term is not 0 either. And so I have to calculate both. And I have to take the dot product into account of E dot dA. I have to take, therefore, have to calculate again the displacement current. So why do it that way? I would suggest here that we take a flat surface. If we take a flat surface, we have nothing to do with the conduction current. We are only stuck with the displacement current. And I suggest that that's the way we're going to do it. So now I'm going to suggest that we use this flat surface. We have to calculate the displacement current anyhow. We have already calculated that. And so that I'm going to use to calculate the magnetic field at that point. So what do I find? I find B times 2 pi r. This holds now for r less than r inside the capacitor equals epsilon 0 times mu 0 times dE dt times pi little r squared. Why little r squared? Because the flat surface here has a surface area pi little r squared. This distance here is little r, which is smaller than capital R. And so if I apply the second term of Maxwell's equations, it is that area that I have to take into account. But we already calculated dE dt. We just did that. That was, if I recall, IC divided by epsilon 0 times pi capital R squared. So what do I find? I find epsilon 0, mu 0, IC divided by epsilon 0 pi r squared times pi little r squared. And that is B times 2 pi r. This r vanishes. I lose a pi. I lose an epsilon 0. And I find that inside the capacitor, B equals mu 0 times the conduction current times R divided by 2 pi capital R squared, the surface area of the plates of the capacitor. And what you see here, this by the way only holds when R is smaller or equal than R, and it is inside the capacitor. Notice that it is proportional to R. It doesn't fall off as 1 over R, but is linearly proportional with R. When you substitute in here R equals R, you better find exactly the same result that you would have found for P2 if you bring P2 just to the point where little r is capital R. The two must be the same. If you stick in here capital R, notice that you get B equals mu 0 times I of C divided by 2 pi times capital R. And that is indeed exactly the same that you would have found if you look at your solution for P2 and you substitute R equals R. The direction of the B fields in all three cases is clockwise when you look from the left and you see the current going away from you. And here are the capacitor plates. So when you look at the capacitor, if these are the capacitor plates and you're looking away, the current going away from you, this E field is growing, then you would see magnetic field here circulating around. It would reach a maximum at a smaller circle, not circus. Its B field is smaller, and right in the center the B field equals 0 because it grows linearly with a little r. So I suggest that I make a plot of B versus R. This is B. Let's first do that for R outside the wire. Let's give the wire an arbitrary radius of little a. If you make it 0, then the magnetic field goes to infinity. And this is the radius of the capacitor plates. So you would get here then a magnetic field which falls off as 1 over r, and this whole curve has the shape μ0 I conduction divided by 2 pi over r. And it stops here at the surface. When you're talking about in between the capacitor plates, then you can go to r equals 0, b equals 0 at r equals 0. It goes linearly, and then it falls off in exactly the same way as it did before. So this curve, this part of the curve here, is exactly the same as that part of the curve. And right here, if you take this curve and you take r equals capital R, or if you take this curve and you take capital R, little r equals capital R, you will find exactly the same result as I just showed you. You find this result with a capital R downstairs. Now we have effectively dealt with all conceivable problems that you can encounter with displacement currents. The only thing we haven't done, which will not add at all to the complication, is we have not had a situation whereby we charge or discharge a capacitor with a changing current. You will see that it doesn't make the situation any more difficult, because you can calculate at all moments in time dE dt. And therefore you can calculate the second term of Maxwell's equations. Now, the fact that there happens to be also a second derivative of E versus T, namely that you have a d2 E dt square, will not make the calculations any more difficult.